Ever wonder about what happens beyond our naked eye?
The things that keep lurking around but can't see?
That sudden rush of wind that passes through your ears.
One word. Gas. From the air we breathe to the farts that kill. Gas is truly a mysterious thing.
Remember the time when your only worry was never letting go of a string attached to a helium balloon? The feeling of panic when you accidentally let go? Thinking that it'll probably went into outer space and maybe someone returned it back your way?
Well, let me tell you, it's never going to happen.
So, pray and tell, where does this go? Where does this red balloon float away to?
It travels somewhere in the world, pops, and falls somewhere lost and forgotten.
In relation to how a certain object, such as a balloon, pops when it is elevated, comes in contact with various gas laws.
In this video, we will be elaborating the factors affecting a balloon or any object that can expand to accommodate certain changes, such as a hot air balloon or a weather balloon.
Concepts according to gas laws ranging from Charles' law, Boyle's law, and combined gas law will be utilized.
Let's begin with the popular gas law, the Charles gas law. According to Charles, the volume of a gas is directly proportional to the temperature of the gas. It states that volume and temperature of a sample of gas are directly related when all other factors are kept constant.
In relation to the helium balloon, a balloon filled with cold helium will not float since it has a greater density than the outside air. So, as the balloon warms, helium will expand and become less dense, enabling the balloon to float.
Oh, now it makes sense. That's why according to Jacques Charles, as the temperature increases and so does the volume.
Well, folks, I hear Robert Boyle justicing on how it wasn't only Charles who had the great law about gases. The other gas law we will be talking about is the Boyle's law.
Boyle's law states that a decrease in the volume of a container results to an increase of the pressure of an ideal gas, and vice versa.
This can be related to the balloon at higher altitudes. As we go higher, the pressure inside the balloon increases and the volume decreases. It can also be applied to the air outside the balloon at a higher altitude. Air becomes thinner as we go higher, meaning there is a decrease in pressure and increase in volume.
This law basically explains the inverse relationship of pressure and volume.
Now, combining these two gas laws, there is a more profound law that can relate all these factors into one law, the combined gas law. It consists of the relationships of temperature, pressure, and volume, and how all these can affect a certain object, in our case, the helium balloon.
It states that pressure is inversely proportional to volume, at the same time that pressure is directly proportional to temperature.
Since Charles' law and Boyle's law can be applied, we can combine these two equations and we'll get the simplified version, which is the combined gas law. This states that when the helium balloon rises, its volume decreases, while its pressure and the temperature inside the balloon increases at the same time.
Since pressure inside the balloon increases, pushing against the elasticity of the balloon, this will eventually result in the explosion or popping of the balloon. According to NASA, they do not fully inflate the weather balloons because as it rises, balloon expands due to the drop in pressure around the balloon.
Now, before we start solving, let's have a recap.
So, in Charles' law, the relationship of volume and temperature are directly proportional. That's why it can be put into an equation such as
For Boyle's law, the relationship of pressure and volume are inversely proportional, which can be further simplified to the formula.
Lastly, for the combined gas law, the relationship of pressure is directly proportional to temperature and inversely proportional to volume, which results to the formula.
Now, are you ready for some problem solving?
yes.
No!
So here we go. A group of friends decided to play with a helium balloon. One of them accidentally let it go, making it rise up into the air until it can no longer be seen. The gas inside the balloon initially has a volume of 0.93 liters at 25 degrees Celsius and a pressure of 800 torr. As the balloon rises up, the volume of the balloon becomes 0.55 liters at 20 degrees Celsius. Calculate the final pressure inside the balloon. Pause the video and try solving it on your own.
So first, let's list the given. Initial volume or volume 1 is equal to 0.93 liters. Initial temperature or temperature 1 is 25 degrees Celsius. Initial pressure or pressure 1 is 800 torr. Final volume or volume 2 is equal to 0.55 liters. And final temperature or temperature 2 is 20 degrees Celsius. Let final pressure or pressure 2 be an unknown since this is what we are looking for.
Now, after listing the given, the proper formula in order to solve this problem is the combination of the gas laws, which is the combined gas law. Using the formula, we can now derive the equation in finding pressure 2.
But first, convert the temperature into Kelvin and pressure into ATM. It is a must. As mentioned previously, the given temperatures are in degrees Celsius, meaning we only have to add it with 273 to convert it into Kelvin.
So, 25 degrees Celsius becomes 298 Kelvin, while 20 degrees Celsius become 293 Kelvin.
To convert torr to ATM, we must remember that 1 ATM is equal to 760 torr. Using dimensional analysis, we can write this as 800 torr multiplied to 1 ATM over 760 torr. Canceling the unit torr, this results to 1.05 ATM. Now, you can substitute the given to the derived formula for pressure 2.
This will yield a result of 1.75 ATM.
Well, there you have it, the presence of gas laws in a helium balloon.
We hope that you learned more about balloons.
You mean gas laws, right?
More like how gas laws are acting on helium balloons.
Well, we hope you learned a lot in the duration of the video. Remember the formulas, and this can help you remember the relationship of the factors involved in gas laws. Thank you for watching.